Hello, and welcome back to our series on Vertex Operator Algebras. In this, our 15th episode, we shall construct a parametric family of modules for Heisenberg algebras. In our next episode, we'll actually show that these are effectively the unique, irreducible ones for a fixed choice of parameter. Let's get started. Recall from last time that a Heisenberg algebra is a Lie algebra whose center is one-dimensional and equal to its commutator subalgebra. We considered Z-graded Heisenberg algebras and fixed the center to be the space of homogeneous degree 0. This afforded a natural decomposition into a triple of abelian subspaces, H+, H-, and H0. The maximal abelian subalgebras of H are either of H+ or minus with H0, which we denote B plus or minus. Our strategy for building an H module is to first build a module for the abelian subalgebra B+. Then we'll use it to induce an H module using the universal enveloping algebra of H. Today, our parameter for all discussions will be some non-zero k in the field F. Define a one-dimensional vector space V sub k, which is essentially the field F. This will serve as a module for V+. The relevant algebra action on Vk is as follows. Z, the basis element of H0, acts as scalar multiplication by k. Additionally, the action of any member of H+ on any vector in Vk simply vanishes. Finally, we require that V sub k be a graded vector space, and any non-zero vector, basically say the unit element, has degree 0. A quick mental review exercise might be to explain to yourself how V sub k can be Z-graded despite only having one dimension. Armed with a B+ module, we now define the H module M of k by the usual induced construction. Which isn't as bad as it looks, so let's unpack this a bit. You might recall that H decomposes as B+ plus H-, and you might also recall from section 11 that the Poincaré-Birkhoff-Witt theorems showed us how this implies that M of k is isomorphic to the simple tensor product U of H- times V sub k, where U is the universal enveloping algebra. Given that V sub k is essentially F, the middle linear product with F is a trivial factor, and so M of k is isomorphic to U of H-. But since H- is abelian, we find that M of k is isomorphic to the symmetric algebra S of H-. In other words, M of k is equivalent to the space of polynomials in basis elements B sub j of H-. If you're familiar with the ladder operators of a Fock space, you might think of these as the space of polynomials of creation operators acting on the vacuum. Okay, so that's a little bit more manageable, no? The H action on M of k comes in three varieties, one for each of the abelian subspaces of H. Let's go through them one by one. Let V be a vector in M of k. From H0, Z on V equals kV. From H-, B sub I on V equals B sub I times V, which is just another polynomial in the B sub I basis. Finally, from H+, A sub I on V, owing to the canonical commutation relations, this can be thought of as the action of k times d by dBi, a derivative on those polynomials in D. This works exactly the same way as the Schrödinger picture of quantum mechanics discussed at the beginning of yesterday's lecture. Evidently, from this perspective, M of k is irreducible, since no subspace of it is entirely invariant under the full H action. In other words, there is an infinite supply of B's to contend with. Whew, okay, and that's our show. Who would have guessed that all of the structure could come from those two simple constraints on the Lie algebra's central subspace? Next time, we'll prove that M of k is essentially the unique, irreducible Heisenberg module for fixed k, which can be thought of as the algebraic cousin of the Stone-von Neumann theorem from quantum mechanics.